So here we have our first homework question. We have three sets of initial and final velocity vectors. And what we want to do is draw the direction of the acceleration vector and describe the motion. So I'll start with this first one here. We see here that initially the object is traveling up. In this case, it's an astronaut. And our final vector also shows the object traveling up, but it is shorter, which means our object is slowing down. Okay, that shorter vector indicates that. And if we're thinking about the direction of that vector, since it's slowing down, it must be opposite the motion of the object, so it's going down. Moving on to question B. For this one, we initially have a velocity vector going to the right, and then we have a velocity vector going to the left. That's our final vector. So this one's similar to one we talked about in class, but the only way for this to happen is if our acceleration then goes to the left. And what's really going to happen, and this is a little bit complicated, but there's a few things that are going to happen here. We're first going to have the object slow down to a stop. And that's what's going to happen in the beginning when the velocity vector is to the right and our acceleration is to the left. That's going to cause the object to slow down. It eventually will come to a stop. At that point, it's going to change directions. And once it's changed directions, it's now going to continue accelerating to the left, and that's going to lead to the object speeding up in the opposite direction, to the left, because in that case, our acceleration vector and our velocity vector will be in the same direction. Moving on to our final case here, we initially have zero velocity, so our object is at rest, and then we have a velocity vector that's down and to the right like that. So the only way for that to happen is if we accelerated in that same direction, down and to the right, because that acceleration is going to lead to a change in velocity in that direction. And the motion, if we're going to describe it, is simply speeding up, okay, in that down and to the right direction, because we go from not moving to moving in that direction. Okay, for this next one, we have to match this described motion, these described situations, to possible velocity and acceleration values. So let's start with our first one. We have an airplane taking off down a runway. What I would be thinking about here is that's got to be a situation where we're speeding up, okay, if it's an airplane taking off. So we have two possibilities where we're speeding up. We have option 2, which shows speeding up because both the velocity and acceleration are in the same direction, and option 4, which also shows that. To distinguish between the two, since this is an airplane taking off, it's probably going to be a high acceleration, so I'm going to go with option 4 here. For B, a person on a bicycle coasts up a gradual hill. In this case, the person is going to be slowing down, so I'm looking for a situation where we're slowing down, which would be option 1, because velocity and acceleration have opposite signs, or option 3. I'm next going to think about this word here, this gradual hill piece. So I know that it's going to be a low acceleration. So of my two slowing down options, 1 and 3, I'm going to select option 1 because that is a lower acceleration. Moving on to the next one, a gentle breeze pushes on a sailboat, making it go a little bit faster. So this is a speeding up case. The only one that I have left here is option number 2. I've already used option number 4 for situation A. And this actually matches here nicely because we have a gentle breeze pushing on the sailboat, making it go a little bit faster. And I see that option number 2 has a relatively low acceleration compared to option number 4, so that matches nicely with that one. And that finally leaves situation D, must be number 3. Let's see if it matches real quick. A car slams on the brakes, so that's going to be a slowing down case, so that matches. 3 is showing slowing down, and it's showing slowing down with a high acceleration, so that matches up nicely with situation D. Okay, so for problem 3 here, we have a motion map for an object. And we're going to answer some questions based off of this motion map. We see it's split into 3 time intervals. We have time 0 to time A to time B, and time B to time C. So the first question that we have is we want to rank the average speed during each of those time intervals. So what I'm going to be thinking about during this time is the average speed is going to be distance over time. So I know that each one of these time intervals are equal in time, so really what I'm concerned with is in which situation do we travel the greatest distance. So that's really all I need to think about. So looking at this, I see from 0 to A, I travel a distance of D. from A to B, I go 1D, 2D, 3D, and from B back to C, I go 1D, 2D. So, if I'm going to go ahead and rank these here, the greatest average speed is going to be from A to B, because I travel a distance of 3D there, and that's going to be greater than my average speed from B to C, where I travel a distance of 2D. But that's going to be greater than my distance from 0 to A, where I only travel a distance of D. And this notation here, this is typically how we're going to do our ranking. Okay, we're going to use inequalities to show which one's bigger. If we did happen to have two that were equal, then we would simply put an equal sign there. But we don't have that in this case. Moving on to part B, we're now thinking about the average velocity during that time interval. So instead of being concerned with distance, we now want to think about displacement, which remember is how far we are from where we started. So thinking about my displacement for for 0 to A, I start here and end here. So that's a displacement of D. For A to B, I start here and I actually end here at 2D. So my displacement is really just from here to here, which is simply D. All right, so for B, from 0 to A and from A to B, my displacements are actually the same. And then from B to C, my displacement is 2D. So if we're ranking from greatest to least, in this case, B to C is actually the greatest because it has a displacement of 2D. Okay, and that's going to be greater than A to B, which has a displacement here of D from here to here, which is going to be equal to that initial displacement, 0 to A. All right. So again, I am ranking the average velocity, but I'm thinking about displacement because that's what's ultimately going to determine that. For the last part, I'm thinking about the direction of the acceleration of the object from 0 to A. So if I look right here, I notice, if I look real close, that these dots are actually getting further apart, which means that my object is speeding up while traveling to the right. Since my object is speeding up and traveling to the right, my acceleration must also be to the right in the same direction as my velocity. And the direction of the acceleration from B to C. If I look here, I see that the dots are getting closer together, indicating that the object is slowing down while traveling to the left, which means that my acceleration actually is still to the right, opposite the direction of my velocity. So in both cases, both from 0 to A and from B to C, my acceleration is to the right. For number 4 here, we have yet another strobe diagram. And what we want to do for each situation, for each time interval, is show the direction of the velocity vector and the direction of the acceleration vector. So we'll start with the interval from A to B. Our velocity vector is, that's not that bad to do. We know the object's traveling to the right, so our velocity vector must also be to the right. And our acceleration vector, we're going to look at what the object's doing, and it looks as though these are actually evenly spaced, which means that we actually don't have an acceleration. So our acceleration simply is going to be 0. For B to C, our velocity is still going to the right. We're still traveling that way. Okay, and thinking about our acceleration, well, it looks like we are actually speeding up some here. All right, this gap is bigger than this one, and this one is even bigger. So that means that our velocity is to the right, and our acceleration must also be to the right since our object is speeding up. From C to D, our final one, we see that our object still is traveling to the right. It looks, once again, though, like these are pretty evenly spaced, which means that our acceleration, just like in the first part, is going to be equal to 0. Okay, so for this one, the past few times we've been given a motion map and asked to analyze it. For this one, we're actually going to be asked to produce our own motion map based off of a description of some motion. So for this first one, we have a box is sliding across the floor to the right and slowing down as it slides across the floor. So we're going to have dots. Let's draw our first one here. All right, and the direction of velocity is going to be to the right. We know what needs to happen is that these dots need to get closer together. All right, continuing to the right though, because we're slowing down. So I'm going to start spacing them closer together. And it tells us to draw at least 5 dots that simply makes things a little bit easier to see. That last one I'm not going to draw a velocity vector for because that will be our position where we're stopped. So there are my 5 dots showing the box slowing down as it travels to the right. Each dot is getting closer together. Okay. And we also need to indicate the direction of the acceleration, and if it's slowing down while traveling to the right, the acceleration must be to the left. The next one, the Tower of Terror, is initially at rest at some height, and it's going to drop, speeding up as it falls towards the ground. So I'll have my initial dot here. All right. We'll say this is the at rest point, so we won't put a velocity vector there. Sometime later, we're going to have a dot here with a little bit of velocity. And what's going to happen is it's going to be the opposite. These dots are going to get more and more spread out as we're falling, showing this Tower of Terror speeding up until we have the greatest velocity on our final dot. So something like that, okay? Don't stress too much about the actual spacing of them as long as you have the general idea showing that the dots are spreading out and the velocity is down. We also need to indicate the direction of the acceleration. So, since we're speeding up while we're traveling down, our acceleration must also be down. For 6 here, we have a number of situations. We need to talk about whether or not it's possible for these situations to exist. So give an example, if not, explain why not. So let's think about this first one here. Is it possible to drive with a constant speed and still accelerate? Keep in mind, we do have 3 ways of accelerating. We have speeding up, slowing down, and we have changing directions. So keeping those in mind, all right, if we have a constant speed, we can't speed up, we can't slow down. However, we still can change directions. So that's the key. For this one, changing directions is going to allow us to have a constant speed, but still accelerate. So the easy example really is just saying that you're turning while maintaining a constant speed in a car. Obviously, there are many, many examples. For B, is it possible to drive with a constant velocity and still accelerate? So let's keep in mind here, just thinking about this conceptually for a second, velocity means speed plus direction. So thinking about that last one, this was really our way around it, was we changed direction. That allowed us to accelerate while still moving at a constant speed. So if we take that away, that changing directions form of acceleration is out. Okay, so this is no, this is not possible. And there are a few ways to explain this. What I would say is that acceleration is the rate of change of the velocity, and that's going to mean the velocity must change in order to accelerate. You also could talk about how velocity is speed and direction. So if we have a constant velocity, we have a constant speed, meaning we can't speed up or slow down, and a constant direction, meaning we also cannot change direction. And that eliminates the 3 possible ways that we can accelerate. Moving on to part C, is it possible to have 0 velocity but still be accelerating? The answer to this one is yes, that is possible. There are 2 examples that I usually think about with this one. The first is that point of changing directions. So that would be like the situation where an object's traveling to the right, slows down to a stop, and then begins traveling back in the opposite direction. So there's many examples of this, but the basic idea is we're going to have the object going like this to the right, slowing down to a stop, and eventually going back in the opposite direction. This point right here, as we're transitioning from going to the right to going to the left, is a situation where we have 0 velocity, but we still are accelerating. All right, as we're traveling to the right and slowing down, all right, we're getting slower, we're getting slower, we're getting slower. At this point right here, right before we start traveling the opposite direction, we have to basically go through 0. We have to have that instant where we are not actually moving, but during that time we are still accelerating. Okay. The other situation that we could do, right, and this one's maybe a little bit trickier to understand, but really anytime we are starting from rest, anytime an object is initially at rest and it begins speeding up, we're going to have a point, we're going to have an instant where we have zero velocity, but we still have an acceleration. In order to begin to move from rest, in order to begin to speed up from rest, an object must accelerate. And it might sound like a chicken and the egg situation. What causes what? Does the change in velocity lead to an acceleration, or does the acceleration lead to a change in velocity? We will answer that question more thoroughly later in the year, but an acceleration is needed to change the velocity. All right, and like I said, we'll talk later about what causes that acceleration. All right, moving on to our final one now that we have a little bit more space. Is it possible to have a decreasing velocity but an increasing acceleration? So this is similar to one we did in class, but I do think it's worth thinking about another possibility in a slightly different situation because this is a tricky one. So the decrease in velocity part means that an object is slowing down, okay? That is what that means. And the increase in acceleration part indicates that the rate or how quickly the object is slowing down is getting bigger. All right, so we're slowing down more quickly than we were before. So if we're looking for a situation, yes, this is possible, and the case would be pressing on the brakes lightly in a car, which would allow the car to slow down, and then pressing harder on the brakes. That would allow for an increasing acceleration, all while slowing down the entire time. There are many other examples. Again, I always think that the car one's the easiest one to think of. Okay, we have another scenario one here. We have a red car and a blue car driving down the highway. The red car is initially behind the blue car as shown here, and we know that the red car eventually passes the blue car. So the question is, at the instant that the cars are passing, is it possible for the red car to be slowing down? Explain why or why not. So the answer here is yes, this is possible. In order for the red car to pass the blue car, all we can say is that the red car's velocity is greater than the blue car. That's what needs to happen in order to pass someone. You must be traveling faster than them. It says nothing about your motion, okay? So if we want an example, okay, so maybe the blue car is traveling at 50 miles an hour and the red is slowing down from 70 to 60. Well, if that was our situation, okay, the red car, of course, would still be able to pass the blue car because the entire time it's still traveling faster. And that really is the key. If we want to sum this up, and there's lots of examples you could give, and that's a nice explanation, you could explain it more on a fundamental level. But the key idea here is that as long as the velocity of the red is greater than the velocity of the blue, red can pass blue. All right, that's what needs to happen. Okay, so we have here to the right the velocity and acceleration vectors for an object at one instant. If the object maintains the same acceleration, describe the motion of the object both in the near future and after a long period of time. So initially, what we're going to think about, what's going to happen with this object right off the bat? Well, first the object is going to slow down, okay, because the velocity and acceleration vectors are in the opposite direction. However, once it's slowed down enough, it's going to come to a stop. And if it continues maintaining that acceleration, what's going to end up happening then is it's going to begin to speed up in the opposite direction. In this case, that would mean going to the right because it was initially traveling left.